And I'm going to share my screen. So, okay, so in this chapter, we're going to introduce the trip distribution model, which would be the second step of the four-step model. And we will focus on the gravity model. And this is actually one of the most popular model applied for the trip distribution. So basically for this lecture, you will see three topics. The first one is the series about the gravity model. Well, I'm gonna give you the all the details about how the gravity model is derived and what's the final equations we have to use. And after that, I'm going to introduce two calibration methods for the gravity model. One is based on the average cost. The other one is based on the it's actually the FHWA method based on the observed cost and the observed cost from each origin destination and the observed trip rate. So let's first go to see the trip distribution. So for the from the previous lectures in the previous step, we have introduced the trip generation model. It helps us to determine how many trips will be generated by each origin, or how many trips will be can be attracted by each destination. But the issue we have to think about is like in the second step is how many trips should be assigned from one origin to one destination. That's actually a very tricky, very important question. We need to determine what's the demand from origins to the destinations. So this is the general trip table. Say that we have Z origin and Z destinations. And from the trip generation model, we will be able to find out how many trips will be generated for each origin, how many trips will be attracted by each destination. But in the trip matrix, we want to find out how many of the trips in each cell of this matrix, which would be the number of the trips from one origin to one destination. And this is the number we have to estimate in the trip distribution step. And if we go to check this matrix for the diagonal, those will be the trips traveling inside of the HTAZ zone. We define them as the intrazonal trips, and usually in the transport planning we have to consider this. But for the modeling part, we will rarely consider their impact because they have less impact to the road traffic conditions. And if we do a summary about the trip along the doing a summary about trip for one origin, you can get the total number of the trips with that origin. That will be the trip generated by that origin. And of course, you can also find out how many of the trips will be attracted by each destination, which is a DJ, and that's the total number of the trips attracted by one destination, J. That will be the summary of the TIJ for the whole column. So this would be the relationship between the trip rate from one origin to one destination and the production and attraction. We call this one. We call we call OI as the production. This is a which means that the trip will be produced at this origin and the DJ as the attraction. That will be the trips attracted by the destination J. So they are also, if we do a summary about all the trips from all the origin to all the destination, that will be total number of the trips from all the TAZ zones, assuming that the total number of trips is a capital T. And it could be the summary of all the values, all the trip rates. TIJ could be the summary of the OI, or could be this sum of dj for all the destinations. So that's the trip table, which would be giving the very fundamental definitions about the what we need to do in this step. And now let's see how we're going to define the gravity model based on the trip table. First of all, we will have the trip table. We will have the trip rate for each origin and each destination. We also know the total number of the trips for the each origin and total number of trips for each destination. And for the origins, we can apply the trip generation model to estimate what's the number of the trips. How many of the trips will be generated by each origin? This is kind of the estimation, it's not the actual value. And similarly, for the destination, we can apply the trip attraction model. We haven't introduced that one in the first step, but basically the trip attraction model is the same to the trip generation model. They will apply different. They will just apply different parameters. For the attraction, they may focus more on the employment opportunities. For the generation, they will more focus on the household structures and income levels. So for the attraction, we can also conduct an estimation about how many trips will be attracted by each destination. And with that, we can estimate what's the total number of the trips in this region with Z TAZ zones. So that is T hat. That's the total number of trips we're gonna do. We're gonna estimate. But in between, with the from the first step of the transport planning, we don't know how many of the trips will be generated from each origin to each destination. That's the part we have to estimate. So with that, we will for this kind of estimation, the TIJ hat, the estimated trip rate from origin I to origin destination to destination J, isn't a function of the demand and supply. That's what we introduced previously, related to the cost of the trip, the potential demand, or the features of the road or the routes. And it's also highly related to the what's the distance from one origin to one destination. So these are actually originally from the direct demand model. We will be able to estimate the number of trips from the origin I to destination J directly. But as for now, we are working on the 4-step model. So we cannot find out in the closed form equation for this function. So we don't know what's the formula of FDIJ SIJ. Instead, we have to use the production, the number of the trips from the origin, and the attraction, the number of the trips from the destination, to conduct the estimation of the TIJ. So now let's go to see how to do that. Before we do that, we also need to define the trip cost matrix, which will specify the cost of the trip from one origin to one destination. And this is a matrix which will cover all the origins and all the destinations. And we assume that the cost from the origin I to destination J it's a CIJK, which is for the mode. K here represents what kind of mode we're going to use. It could be driving your own car, could take the bus, or walk, or taking the bike, and so on. This is the cost matrix we defined. This kind of cost is actually determined by a lot of factors, including the monetary cost. If you're taking a bus, you need to check what's the fare rate of the bus ticket. And of course, you need to think about the travel time, how long it's gonna take from one origin to one destination, and the inconvenience, like usually the driving your car is more convenient compared with the bus. And riding the bike is even more convenient because you can ride a bike at any time and arrive your destination at some place which are very close to destination. But for driving your own car, you need to find out some parking space. So all these factors should be considered as the cost. But in general, if we want to simplify the analysis, we can just think about the travel time. Like for most of the transportation planning study, we simplify the analysis of the cost to use the travel time to represent the cost of the trip. So we will also apply these ideas in this lecture. So we assume that letter Tijk represent the cost of the travel time of the trip from the origin I to the destination J using the mode K. So that's the assumption we made for the trip cost. And now the next thing we're gonna need to think about is what's the gravity model, and what's the how we can use the gravity model to find out the distributions of or to assign the trip for each origin and each destination. So let's start with the trip matrix. We have the attraction, which would be the dij. We have the production, that would be the OI for each origin and each destination. And we also know the total number of the trips, say it's a capital T. And now let's take a look at one example. Another thing I forgot to mention is like the T will be the summation of all the trips in the trip matrix, and is also the summation of all the production and summation of all the attraction. But let's take a look at one example. Assuming that for this Z TAZ zones, we only have 5 trips, so capital T equal to 5. So the 5 trips would be T1, T2, T3, T4, and T5. And we also see that for the trips from origin I to the destination J, the number of the trips would be 3. So we know Tij equal to 3, and capital T is a 5. Now we have to identify how many possible ways for us to assign a trip in the cell Tij. So we have 5 trips. There are 5 different trips, and we need to assign 3 trips in the zone in the cell Tij. So the total number of the combinations would be determined by these 2 values, 5 and 3. So if we go to check the combinations, first of all, we definitely can find out the T1, T2, T3 as the 3 trips in the cell Tij. We can also find out another combination, T1, T2, T4, as another combination. And if we go to explore all the possible combinations, eventually you can find out 10 possible combinations of the trips for the cell from I to J. And this actually comes from the assumption that we have 10 trips, and 3 of them will be assigned to the cell Ij. And if we go to check the general situations, say that we have n trips, and k of them will be assigned to the cell I to J, then the total number of ways for us to assign a trip would be C. This is a C and K. So it gives you the value as n factorial divided by k factorial times n minus k factorial. So n here is the total number of the trips, and k is the trips assigned to that cell. And this is for one. This is just for one cell. So we have say that we have W different ways for us to assign the trips in that cell. And if we extend this one to all these cells, or the Z by Z matrix, we can then identify the total number of the possible ways to assign the trips. Before I go to that, I will give you some introductions about what's the meanings of the CNK. So for the CNK, it defines what's the possible ways for you to take k different objects from a sample of n objects. So that's the possible ways. So for the example of C53, so this is a C53. So it's a 5 factorial divided by 3 factorial times 5 minus 3 factorial. So on top, that would be 1 times 2 times 3 times 4 times 5. At the bottom, that will be 1 times 2 times 3 times 1 times 2. So you can quickly find out the result as 10. So there are 10 different ways for you to assign a trip for that example. And regarding to the general case, that will be the CNK. And now if we go to see all the cells, we can try to identify how many trips we're gonna assign for all the origins and destinations. So we will keep this one for the general case. If you have n trips and you want to take a k for them, so the total number of the ways would be CNK. And now if let's start with the first cell, T11, assuming that we have total number of trip of k, and T11 would be the number of the trip assigned to the cell from the origin 1 to the destination 1. So the number of the ways for you to would be CT T11. So that is a T factorial divided by T11 times T minus T11 factorial. So that's the first situation. And now if we move to the for the second number, if we go to the second cell, assuming that there are T12 number of the vehicles assigned, so the possible ways for us to assign the rest number of the trips would be C. So as we have already assigned the T11 to the first cell, so the available trips left would be T minus T11 to T12. So that's the this equation will give you the possible ways for you to assign the number of the trips in the second cell. And then the total possible ways for you to assign the trips to T11 and T12 would be the product of WT11 and WT12. So that would be the product. So this is what we get for the two cells. So that's just for two cells. If you try to check all the Z by Z cells, you can find out the total number of the possible combinations. So what we can summarize is like for all these Z by Z cells, that will be WT11 times WT12, WT13, until you get WTZZ. And now let's expand this equation. So you can get the detailed formula for the WTIJ, which would be the total number of the possible ways for you to assign the trips in all these Z by Z cells. So you get this very complicated equation, but if we go to check the details of this equation, you can find that you can quickly remove all those items from the equation and eventually you're gonna find out in a very simple equation. I'm gonna exclude all these details. So basically, after you do some simplification, you can find that the total number of the possible ways for you to assign the trip to the z by z cells is t factorial divided by t11 factorial times t12 factorial, and do this production for all the cells until you get a tzz factorial. And we can simplify this one as t factorial divided by the products of I from 1 to z, from j from 1 to z for tij factorial. So this is the total number of the trips we're going to assign from for the total number of the trips t to the z by z cells. And for the gravity model, what we want to do is like we want to maximize the possible the ways to assign the trips to all the cells. But we can start with a simple case, assuming that we don't know the production, we don't know the attraction, we just know the total number of the trips from all the origins and all the destinations. We also know the number of the ways for us to assign the trips to this all the z by z cells. For the gravity model, we're going to try to maximize the number of the ways to identify what's the optimal value of Tij to maximize the number of the ways. That's what we call the gravity model. We will always try to maximize the possible ways to assign the trips. And also they have to satisfy one constraint. If you summarize all the trips in all the cells, they should be the same to the total number of the trips. So that's the physical rule we have to follow. And now we can see how. Yes, question.
Sorry, I just didn't want to interrupt you, but I have a small question. The t that we know, do we know it from the previous step, like from the generation of trips? Is that the number that we get from step number 1?
Yeah, so it will be well from the generation step. This is a little bit different. We will cover all the different situations. For the generation step, you will be able to know what's the O1, O2, right? Something like that. If we know that, you can calculate what's the total number of the trips. But sometimes, if we are doing planning for the city and city don't tell you the what's the exact number of the trips for each origin or for each destination, instead they just tell you the total number of the trips for the whole city, then you can only use this condition, like you are provided with the value of capital T. So that's the first assumption. We will also go through the other assumptions, like if we are only provided with the value of OI, or if we are only provided with the value of the DJ, or if we are provided with both informations, how are you going to deal with that? So we will go through all the possible combinations.
Okay, perfect. Thank you, Doctor. And just one small question. In slide number 5, there's a small t, small t1, small t2, small t3. What are these?
Oh, the little t represent the travel time from the destination J. So that's different. Okay. It's a little bit confusing, but well, in the future we will probably refer them as C to represent the cost of the trip.
Okay, I see. Okay, yeah, thank you.
Okay, good. Okay, so now let's go to see the part about we have this maximization optimization problem. We want to find out what's the optimal value of Tij to maximize the possible ways with the constraint that the summation of Tij equal to capital T. And to do this derivation, well, of course, this derivation is very complicated. So first of all, we're gonna do the log transformation. And this one will help us to convert the this kind of products to some subtraction and the addition information equations. And if we do this one, do this kind of log transformation, you can get simplified equation, but still you have something called the factorial, right? The factorial is also a little bit difficult for us to do the to handle in the optimization problem. So first for these products, the product from I to J, the product from J to Z, from I from 1 to Z and J from 1 to Z could be converted to the summation directly based on the feature of the log transformation. And we also want to cite the Stirling, a formula called the Stirling formula to change the log x factorial to some simplified equation. So usually for the Stirling formula, log x factorial will equal to x times log x minus x. So with this kind of simplification, the equation in the summation, the component in the summation will be much simpler for you to find out the optimal solution with the Lagrangian equations. So here I'm just gonna show you the derivations quickly. So we do all these transformations, and with the Lagrangian transformation, Lagrangian equifactors, you can try to combine the constraint and the maximization problem together. And then what you need to do is just trying to find out the first order partial derivative for all the values, all the Tij's, and the Lagrangian factor lambda. With that, you can go to, well, I will skip the details about the derivation. If you are interested about how to get the result, you can check the details. Check all the details in this course notes. So do the derivations for first order partial derivation, and try to apply some simplification, and eventually you can find out a very simple solution for this optimization problem. And I will skip these steps. So basically, after all these derivations, you get one equation, minus ln TKL minus lambda equal to 0. So this it means that you're gonna have the very simplified result. So with that, you can find Tij equal to exponential minus lambda. And you know that lambda is not related to I and J, which means that for all the cells, it will have the same value. And also, you can go to check the constraint of this optimization problem. The summation of Tij will be the same to capital T. So with that, you get the exponential of minus lambda is a T divided by Z squared. So this means that for all the cells, for all the origins and destination pair from I to J, the total number of the trip assigned to that cell will just be T divided by Z squared. So it indicates that the trips are uniformly distributed for all the cells. So that is a T divided by Z squared. This is the case for the this is the unconstrained situation where you don't know the origin information, you don't know the destination information. You just get the total number of the trips, and with that, the best distribution model is like you will set the same number of trips for all the origin and destination pair. So that is T divided by Z squared. And with that, you can find out what's the value of the OI basically that will be T divided by Z. And similarly, you can find out the value of dj is also T divided by Z, which means that they are uniformly distributed. So that's what you get for the distribution with respect to the unconstrained origin and destination conditions. You don't know the production, you don't know the attraction. This is the very extreme situation, like you don't know anything. But for the in reality, if you have some if you have already conducted trip generation step, you will be know some information about the origin or the destination. So let's go to the second situation. If you know the productions of the of all the TSZ zones, which means that you know the value of OI, but you don't know the value of DJ. So this is called the production constraint gravity model. And of course, you can find out the value of capital T. The capital T is the summation of OI. So that's what we assumed for the second situation. And we want to find out what's the values of the Tij under this model, the production constraint model. And still, we want to maximize the number of the ways for us to assign the trips to each cell. And now we have two constraints. First of all, if you do the summation about all the trips from all the origin destination pairs, you will find out the total value is capital T. And also, if you do the summation for each origin, say that the origin I, then summation of the Tij will be OI. So sum of this whole column, whole row, you get the value of OI. So that's the constraint. That's the constraint we set for the production constraint gravity model. And now let's see how we can find out the optimal assignment of the trips under these conditions. And we know that the first one is it comes from the gravity model, and for the constraint we actually have Z constraints, even though it's written as the same format. But we know that this constraint applies for all the Z origins. So we have Z constraints, and now we can also do the first we'll also do the log transformation to simplify the analysis, and similarly apply the Stirling's formula to convert the factorial to some regular numbers. And then we're going to use the Lagrangian equation to conduct the optimization problem. So here we have to know that there are Z different constraints. So we have to assume Z different Lagrangian factor, say that is a phi I for the for each constraint. So this is this one will give you the Lagrangian equation. And now you can just work on the first order partial derivative to find out the optimal solutions. So first order partial derivative for the trip rate and first order partial derivative for the Lagrangian factors, there are Z equations. And now you can go to dive into the detailed derivation. Again, I'm going to skip the details. If you are interested about how it's conducted, try to go through the course notes after the class. And if we go through all of those steps, eventually you will also find out a very simple equation. So for the TKL, you get the minus ln TKL minus phi k equal to 0. You also have the constraint OK minus summation of TKJ equal to 0. And with this, you can find that for all the trips on the along the with the origin k, the rate is exponential of minus 5k. And also you have the summation of TKJ equal to OK. You can then calculate what's the value of the exponential minus 5k, and basically you get the exponential minus 5k is OK divided by z, which means that the trip should be uniformly distributed along all the destinations with respect to one specific origin. And I'm going to show you how it's shown in the trip matrix. So we have TKL equal to OK minus Z. And in this trip matrix, you will find that for each row, the value will be the same. They'll all be the OI divided by Z. And if we do the summation for each column, you can find that the attraction will all be OI, which would be the average value of the trips from all the origins. And that's the result, the best assignment for the production constraint gravity model. So what you have to remember is like the trip will be uniformly distributed along each row, but for each column it will be not. They will not uniform distributed. Instead, it's proportional to the total number of the trips you observed for each origin. So that's for the production constraint gravity model. And the next model is for the destination constraint gravity model. So in this case, we know the value of the attractions for each destination, but we don't know the value of the productions for each origin. So this is what we have. We don't know OI, but we know DJ. And this one is quite similar to what we derived for the production constraint gravity. Instead we just change the unknown variables. So to do the derivation will be very similar to the production constraint gravity model. So we can skip most of the steps. So if we go to follow the same procedure, apply the log transformation, Stirling formulas, and Lagrange equations, and do the final estimation for the optimal values. What you will get for the optimal assignment, we have TKL equal to DL divided by Z, which means in this case you will see that for the destination constraint gravity model, the trip rate for each column will be the same. There will be the average value of the DJ divided by Z for all the value for all the origins. And for each row, they will be different. This one is proportional. Each row is proportional to the trip rate attracted for each destination. So we can only see that for the production, if we only have the attraction result for the production, they will be uniformly distributed, and they will all be D bar. That will be the average value of all the DJs. So this is just the symmetric to the production constraint gravity model. So that's the two imperfect model. Well, you will either miss the production information or miss the destination information, the attraction information. But in real world, in real world transforming planning problem, you will usually be provided with the both production and attraction. So you know the value of OI, you also know the value of DJ. In this case, we will need to think about how we're gonna assign the optimal trips to each cell. And with that we can still follow the same steps, but instead of only apply one kind of the constraint, we will have to apply the constraint for both origin and destination. So both of them should be satisfied. And then the derivation will still be quite similar. We have to apply the log transformation, but here you have more constraints, and which means that you need to have more Lagrangian factors applied to include all the constraints. So that with that you will have the Lagrangian factor of phi I for the origins and tau j for the destinations. And we need to find out what's the optimal value of Tij and what's the optimal value of phi I and tau j. So still, we're going to do the first order partial derivative to find out the optimal solution. It will be applied to Tij or TKL for all the origins and destinations. You also need to check find out the partial derivative for phi k to represent the constraint for the origin, and tau L for the constraint with respect to the destination. And again, I say that the communication, the derivation is the derivation is very complicated. So you can go to check the whole derivations after the class, and I say that I will only show you the final equation, the optimal equation for the Tij. So follow those steps, and you can find out TKL equal to exponential of minus phi k plus tau L. So this one is related to the both origin and destination. And also, if you go to check the total number of the trips for each origin, we have the first constraint, and if we put them together, you're gonna get the value of exponential minus phi k, that is OK divided by the summation of exponential minus tau j. And similarly, you can get the find out the value of exponential tau L minus tau L for the destinations. And if we put them together, you can get the ultimate expression of the TKL. So it's still, I say that it's still the derivation is very complicated. So just try to go through them after the class. And you know that for this equation at the bottom, it's in the constant because they summarize from all the j's and for all the i's. So for this region with z origin, z origins and z destinations, this would be the constant value. So you can simplify them as a times OI for the TKL, that will be A times OK times DL. And also, if we go to check the constraint for the whole region, so the summation should be T, which will give you the value of A as T divided by the summation of OK and DL. So that will give you some summary about the TKL. what's the TKL? TKL is OK times DL divided by the summation of the OI times DJ times T. And this part is constant. And now you can go to the we can go back to the triple matrix. And we know the expressions of the TKL, apply them to the triple matrix. So we have for the cell 1 is A times O1 times D1. So the triple rate is only determined by the production in the origin 1 and the attraction in destination J. If we go to check all the other cells, it will be the same for the IJ. I'm sorry, this one should be DJ. For the IJ, it's only determined by OI and DJ. A is the constant value. It's not related to the individual TAZ zone. So that would be the double constraint gravity model. We know the production, we know the attraction for each centroid. And the ultimate gravity model we have to consider is the double constraint gravity model with the budget constraints. So here we will not only need to think about how many trips we have to assign for each cell, we also have to think about what's the total cost of the trip. So in this kind of model, we assume that the cost of the cell I or cell I to J as Cij, and we have the budget constraint. The total budget for all the trips in this Z by Z matrix would be capital C. So ideally, we want the total money you spend or total time you spend should be less than capital C. But due to the insatiable conditions, we have to make sure that it equals to capital C. So the summation of the Cij times Tij will be will equal to capital C, and Cij is the generalized cost from zone I to the destination J. So this would be the assumption, and now we have to summarize the problem we want to formulate. We have to formulate all the equations for this model, the doubly constraint with the budget constraint. So first we want to maximize the number of the ways to assign the trips to all the cells. We have the production constraint, we have the attraction constraint, and budget constraint. So 3 different types of the constraints. And again, we will do the similar process to find out the optimal assignment, apply the log transformation for the number of the ways, and introduce the Lagrangian factors to include all the constraints. And then we can do the derivation. So again, I will just skip the very complicated steps, and eventually you can find that for the doubly constrained gravity model with the budget constraint, the expression of the Tij or TKL is very simple. It's a exponential minus 5k. This one is only related to the origin k. Exponential of minus tau L. This one is only related to the destination L. And exponential of minus mu times CKL. This one is related to the cost from the origin K to the destination L. And with that, we can do some further simplification to link back to the production and attraction we observed or we calculated. So with that, with these 2 constraints, what we observe, like for the ultimate for the ultimate expression of the TKL, that would be TKL will be AK times OK times BL times DL times exponential minus mu CK, and you can find out the expression of AK, which would be the showing this equation, and you can also find out the expression of BL that is only related to the it's only related to the factors in the destination L. So that's the final optimal assignment of trips for the for this model, doubly constrained gravity model with budget constraints. And here, obviously, you can see that there will be a lot of information we have to think about, especially if we consider this model. We have to calibrate the value of AK. We have to calibrate the value of BL and also mu in order for us to use this model. And the calibration of this model is not that easy. But we in this class we will still introduce the way about how to calibrate them effectively. Usually for this kind of calibration problem, it's not easy for us to apply some theoretical models or theoretical method to do the calibration. But we can apply some numerical models to do that. So with that, I'm gonna show you the first calibration model for the gravity, first calibration method for the gravity model. But before I jump to this part, do you have any questions about the theoretical the theories of this model?
Doctor,
Yes.
I have a question.
Yes, yes.
I got a little bit confused between IJ and KL.
Yeah. They are the same thing. Here, for all this, if we go check the details of derivation, we intentionally change the index to make sure that there's no confusion. So they will be the same thing. So here for this one, for this formula term, K represents the origin K, L represents destination L. And if we go to check the here, that will be the destination J. It's the same thing. It's just the same thing. We use different symbols to avoid any additional confusion. This is quite commonly applied for the derivations, especially when there are a lot of variables we have to consider.
Okay, perfect.
Professor, I had one question.
Yes, yes.
So we are only considering balanced problem, right? What if there is the total number of trips in origin is not equal to total number of trips in destination?
So this is the case for the perfect situation. The summation of the origins and will be the same to the summation of destinations. But in reality, if it comes from two different models, the trip production model and trip distribution model, they are not balanced. You need to find out a way to balance the demand, the origin destination. Either you can increase the low one proportionally, or try to adjust them proportionally, or to find out the average values of the unbalanced production and attraction. In order for you to use the gravity model, you have to first make sure that they are consistent.
Okay.
So, Professor, I'm a little confused with the meaning of mu.
What value? What variable?
Mu.
Mu. Oh, mu is the it's another factor we have to calibrate. It's the if we go back to the derivation. Let me go to see. So mu. Here you can see that mu is the one. It's a Lagrangian factor we applied for the budget constraint. For this problem, for this model, there's only one budget constraint. There are z destination constraint and z origin constraint. So you have phi I for origin, tau j for destination, but there's only one mu for the budget.
Oh, yeah. So it's just like a constant in the Lagrangian equation for every constraint. Mu is for the budget constraint.
Yeah, it's
We
a constant. It's a constant. It's a constant for the for one model. For each model you calibrate. So if basically for the calibration model, let me try to get this. For the calibration work, you have to find out what's the value of AK, BL, and mu. So of course AK you have z different values. BL you also have z different values.
Yeah.
But for mu you only have one value.
Yeah.
Okay. Well, you will get a better ideas about how we get those parameters in the gravity model for the in the calibration part. So with that, I will jump to the calibration. For the theory, you just try to understand, remember the conclusions we get from the derivation. The details about derivation is not necessary for you to remember. It might be quite useful for you to conduct some research in the future if you have some similar research in this area. This kind of equations will be very helpful for you to find out the optimal solutions with a lot of unknown variables. Okay, so now for the calibration of the gravity model, we start with the first method with the average cost method. So for the calibration, we will calibrate the doubly constrained gravity model with the budget constraint. So we have the expression of Tij, that is Ai times Oi times Bj times Dj times exponential minus mu Cij. So here you see we change the index. It will just be the same thing. So we know the expression of Ai, we know the expression of Bj, and those are the parameters we have to calibrate, and also there's the parameter of mu. And for the value of Oi, Dj, and Cij, Oi is the production, Dj is the attraction, and Cij is the cost. Those in order to do calibration, we know all these values. But for the other variables, Ai, Bj, and mu, we don't know. That would be the part we have to calibrate. And to do the calibration, for Ai, it's actually associated with the constraint for the origins, and Bj is associated with the constraint for the destinations. So basically, you can actually apply the Tij for this the full expression of Tij in this equation, and to conduct the estimation of Ai. So if we apply these two constraints, what it will get is like for Ai, it will equal to 1 divided by the summation of Bk times Dk times exponential minus mu Cik. And similarly, you can find out the expression of Bj, which is related to Ak, Ok, and exponential mu Ckj. So which means that if we are provided with the value of b and mu, you can find out value of a. If you are provided with the value of a and mu, you can find out value of bj. And this kind of iteration we're going to use to find out in the calibration to find out what's the value ai, bj, and mu. So let's go to see more details about the calibration. So this is all the equations we're going to use. And you have to always remember these three equations in the calibration process. And we are provided with the true matrix. We know the value of OI. We know the value of DJ, but we don't know what happens in between. And now for the cost matrix, we know the value of Cijk for the model, for the transforming model K. Or we say that we know the travel time. So just give you a reminder, like for most of the transforming planning problem, we use the travel time to replace the cost. And now with these two informations, we want to find out and calibrate the values of AI, BJ, and mu. To do that, we will first need to find out the actual average cost of all the trips. So the average cost can be calculated by this equation. You first need to find out the total cost for each cell. That will be the Tij times the Cij, and then summarize them for all the cells. And then you need to divide them to the total number of the trips. That will be the which would also be capital T. And this will give you the average cost. So that's the first step, calculate the average cost. And now the next step you need to know is about the assumptions we made. We know the origins, all the origin values. We know all the destination values. And we also know what's the total values of the trip. So we want to use this model. We want to find out the value of AI, BJ, this is the calibrated value, and mu hat, those are all the calibrated value. To find out what's the trip rate for each cell, that will be the Tij hat. This would be our estimated trip rate for each cell. This is our outcome of the calibration. And if you have the calibrated trip rate, you can then find out the predicted average cost. Predicted average cost. This one is not the actual one. That's the C bar hat. The C bar hat is calculated based on the estimated trip rate and the trip cost. Cij here is always the true value, but the Tij hat is the estimated value. So with that, we have the average, the estimated average cost, and for our calibration method, we want to find out the value of mu hat. To first find out the value of the mu hat, to make sure that C bar hat is close to the average cost, to the true average cost, and we will then calculate the AI hat and the BJ hat to make sure that they satisfy the constraint for the origins and destinations. So this would be the two key constraints we have to use during the calibration. I know it might be quite confusing, so I will give you the detailed steps. So first of all, what we do is like we have to set an initial value of mu. Say that it's a mu 0 hat. This is the initial value we set by ourselves. And once you have the mu hat, mu 0 hat, you can compute the initial value of the average cost. So that is C bar hat. In the initial value, we say that is C0 bar hat. And then we can calculate the AI and BJ to satisfy the origin and demand constraints. And once we have the AI and BJ value calculated, and we can then estimate the trip rate and use the trip rate, estimate trip rate to revise the value of the mu. So revise it from the initial value. We can use this equation based on the average cost to update it. We can also use another more complicated equation if we have more steps that are updated to find out what's the value of the mu for the next iteration. And then we're gonna do the iteration, repeat this iteration again and again until we find out that the estimated average cost is similar to the true value, and the updated value of the mu hat at the two iterations will be the same to each other. So that's the the whole procedure. And I think we have already passed 1 hour 10 minutes. I want to stop here and give you a 10 minutes break. And after that, we're gonna continue the introduction of the calibration procedure. At this point, do you have any questions? Okay, if we don't have any questions, I will take a 10 minutes break. We're gonna resume the lecture at 10:40, and I'm gonna mute myself and turn off my camera. Okay, I guess we can resume the meeting. It will be very confusing for those equations, and I hope for the following examples you will have some ideas about how to use the gravity model. So let me just try to give you an additional background information, and then we can start the the detailed example. Bring to the front. Okay, so here we have some initial guess. You know that in the first step, we need to check what's the initial value of mu, and the initial value is very important. So we have to find out the appropriate value of mu hat for the initial step. With that, we can consider that from the infinite urban area, they will all be uniformly distributed for all the origins and destinations. This is our assumption. If we don't have any information about it, we can assume that they are uniformly distributed. And then with that, if we know that for the trip, like we know the trip from I to J, which means that if we are provided with the origin I, and the trip to the destination J will follow the distribution that one is proportional to the component of exponential mu Cij. So this is the part. It's this part. And if one distribution follows this format, then for the fixed origin destination, Cij is the constant value, say that is R. With that, we can then go to check all the origin destinations, and as this is proportional to exponential mu R, then you can simply apply the constant term ahead of the exponential component. And with that, if we want this one to be an exponential distribution, it means that the integration from 0 to infinite will be 1, and you can then quickly find out the value of g. With this equation, capital G will be mu. So you will see the distribution of the trip rate from origin I destination J will follow the exponential distribution, and this is the equation for the exponential distribution. And for this exponential distribution, the average cost would be the mean value. And if we try to check the mean value of this exponential distribution, well, here I'll give you some details about how to calculate the mean value, and basically with all these equations, the mean value of the cost would be 1 divided by mu. So which means that you can choose the initial value of the mu as 1 divided by C bar, which would be the inverse of the average cost, the true average cost. So this is our initial guess. So with that, what we do is, like, first of all, we will calculate in the example. For this example, if we are provided with the trip rate, the trip matrix from say that is a 7x7 matrix. You are provided with trip matrix. You are also provided with the cost matrix. You can then first calculate the average cost. We have provided the average cost function. So do the calculation, you find out the average cost is 12.2 minutes. So that's the first step. And then for the initial guess of the mu, that is 1 divided by C bar, which is 0.082. So this is the initial guess of the mu. Well, I guess there is something blocked my screen. Just a moment. Let me try to do some adjustment first. Okay. Still recording. Why is it still blocking? So let me exit the sharing and resharing again, so that hopefully it won't be blocked. The part of the screen will not be blocked. Okay, and okay, good. Okay, looks much better. And now in the example, we will go to the second step about how to update the value of AI and BJ. So this is the equation about the estimated trip rate from origin I to destination J, and we have already found out the initial guess of the mu. And in this example, the initial guess of the mu is 0.082. And now we're going to use this information to first calculate the value of A. For the calculation of AI and BJ, we can first make an assumption about the value of AI, assuming that the initial guess of AI are all 1, and then we can recall this equation BJ. We can recall this equation BJ to calculate what's the value of BJ should look like. Here we know the value of AK, which is the initial guess. We OK here is provided is observation, and we also have the initial guess of the mu0 and the value of CKJ, which would be the cost. So with this information, we can calculate the value of B1, and now with the B1, the first iteration of the B1, we can then calculate the value of A1. So for A1, we know the value of is related to BK, it's related to DK and mu0. So we know the value of BK, which is from the third row here. And we also can find out all the values of the attractions for DK. This is from the observation. And we also have the value of CIK. With that, we can get we can update the value of AI for all the values for all the cells, and then repeat this whole process again and again. So do this iteration, you get a B2 and A2, B3, A3, and do the iteration until you find that the difference between two iterations are small enough. For example, for this case, if you find that these two values are almost the same in these two iterations, then you can stop. And then this would be the value of AI and BJ you estimated from the first round of the calibration. So what do we get of the A and B, and we have the initial value of mu. And with that, you can get the estimated true matrix Tij based on the value of A, B, and mu. And this is the estimated value. But obviously there are some difference between the estimated value and the true values. You can make a comparison about the estimated value and true values from the first round. Well, I'm going to show you the comparison later. So this one is not close to the observed value, so we have to continue the calibration. So in the second step, we will do some updates about the value of the mu. So we're going to use this equation to do the update. And in this equation, we actually will go to the mu1. Mu1 will equal to C0 bar hat divided by C bar times mu0 hat. Mu0 hat is the value of mu in the previous step, which is 0.082. And the C0 bar hat is actually the average cost based on the average cost based on the estimated trip rate. And the C bar is always the true average cost. In the previous step, we actually can calculate the average cost based on the estimated trip rate and the cost rate, and that one give you the value as 11.02 minutes. So we applied to the update directly. You get a mu1 hat as 0.073, and then you can repeat the previous process to calculate the value of AI and BJ. So to do this calculation, have the initial guess about the A first, set them as 1, and then you calculate the value of BJ, and then repeat the iterations until you find that the values at 2 iterations are similar to each other. So again, you might need more iterations, you might need less iterations. Just try to check whether they are similar to each other. Like their difference in these 2 iterations are smaller than certain value, or they are exactly the same. And then you can repeat this process again until you find that the mu hat is it's also similar from the at 2 iterations. So in this case, for mu1, we get is 0.073, and then we can do another calculation to find out the well, you can also try to get the C bar hat to calculate what's the C bar hat with the estimated cost, and find out the value of the mu2 hat, and try to check whether mu2 hat is close to mu1 hat. If it is, you're gonna stop the iteration. If no, then continue the iterations until you find they are close to each other. In the example in this lecture, we are just stop at the second iteration. So in that sense, you can well, we can try to check what's the result we observe, what's the calibration results. So this is the figure. The table here shows the observed trip rate, and this is the calibrated trip rate based on the value we show in the second iteration. And you can see there are some difference between the observed and the calibrated values. To make a comparison, we're gonna use we can use the absolute errors. So the error could be is the estimated value minus the observed trip matrix. So this one shows the error matrix. We can also use the square error, which would be more appropriate for us to make a comparison about 2 different calibration methods. So for the square error, we can find out the total sum of the square error would be 452, and the mean square error is around 9.2. Mean square error is one of the useful matrix to determine the accuracy of the estimated value and the observed value. So that's the first calibration method. The method we use the we use the doubly constraint gravity model with the budget constraint, and we calibrate them with the average cost. And with the summary, we find the true average cost. The true average cost is 12.2 minutes, and our initial guess is 0.082, and we have the first updated average cost at 11.02, and then we're gonna apply this kind of iterations to get the value. We have the first one. We have the first in the first iteration we have the mu value as 0.073. We have the we updated the average cost accordingly, and then we can update the equations for us to estimate the trip rate. And as I say that, we can do iterations again and again until we find that this one mu m hat is close to mu m minus 1 hat. For the well, there's another homework to assign for you to do the calibration by yourself, and in the homework you need to do more iterations compared with the example here. So that's the first example. Do you have any questions about this one, about this calibration method with the average cost? Any questions? Okay.
Just one question, Professor.
Yes.
Will this be on the midterm?
Oh, this is not in the midterm. This is the midterm will only cover the lectures from the start of the term to the lectures last week.
Okay.
Yeah. Okay. Okay. If there's no questions, I will jump to the next method. It's a more general method, which is called the FHW BPR calibration method. This one is developed by the U.S. Federal Highway Administration. It's also the method applied for the gravity model, but it has different assumptions to the one to the method we introduced previously. In this method, we actually will introduce the new term, which is called the trip length frequency distribution, TLD. With the observed trip rate and the cost, we can find out the observed trip length frequency distribution, OTLD. And this is the table. This figure shows the distribution. It shows the percentage of the trips in the calibrated area under different travel time. So each bin represents one kind of the travel time. So in this example, you have the travel time between 0 to 5. How many trips you observed in the calibrated area? From 6 to 10 minutes, what's the percentage of the trips in the calibrated area? From 10 to 15, 16 to 20, and so on. While you also can define the size of the bin by yourself. So this is the observed trip length frequency distribution. It comes from the trip table, and the trip table and the cost table. So in this distribution, one of the most important term is the label bins. So which would be the bin value, the bin is specified for the trip rate, or for the travel time, and you have 1, 2, 3, 4 until the maximum number of the bins is specified. And then we from the previous from the previous analysis, we have from the analysis of gravity model, we have the trip rate as a function of the origin, which will be the production, the attraction, and also the function of the cost of the trip from the origin I to destination J. But here, from the average cost calibration method, we assume that FCIJ is an exponential distribution. This is what we assumed from the previous one. This is the average cost method. We assume that it is exponential distribution, but in reality, this kind of functions might not be an exponential distribution. It might be some random distribution, any kind of distributions. So in that case, we want to find out the more general expressions for FCIJ. So this one will brings us to the a new formula, which is applied for the FHW calibration method. And in this method, they assume that the distributions of the trip with respect to the trip travel time follows a discrete distribution, and which would be the trip length frequency distribution, and we can find out the frequency of each beam, and in this equation, tau ij represent whether the trip travel time falls in this beam. If the travel time falls in this beam, in the beam k, then it will be 1. If it's not in the beam k, that will be 0. For example, if one trip has the travel time of 8 minutes, then it falls to beam 2, and so that is a delta ij2 will be 1. But for all the other beams, delta ij1, delta ij3, delta ij4, they will all be 0. So this equation shows the distribution of this trip length frequency. And so that's the assumption about the FHWA calibration method. Instead of using the exponential distribution, we are using the discrete distribution. And so here we can go to check the process about the FHWA calibration method. Basically, it has some similarity to the average cost calibration method. So the equations shown in this yellow box will be all the formulas we have to use for the calibration. First of all, we have to in the calibration we have to make an assumption about the parameters. We assume that the value of fk, they will all be 1s in the first step, and then we're going to need to use this information to find out the value of ai and bj. So we will using the fk, the f0k to do the calculation. First of all, we have to find out ai with this equation, and this actually comes from the original formula, Tij equal to ai times oi times bj times dj times fcijk. And also we have the formula for bj. It's only related to the value of a, o, and the function of the fcij. And now we will calibrate the value of ai and bj in the second step and calculate the value of the tij hat. With that, we can then estimate using the estimated Tij hat to estimate the gravity model estimated trip length distribution trip length frequency distribution. This one is a estimated value. Estimated distribution, and that comes from the Tij hat. For the OTLD, it comes from the Tij, which would be the true value. So that's the difference of these two distributions. And next, before we go to the next iteration, we have to update the value of the f. So we're gonna need to use the observed trip length frequency distribution divided by the gravity model estimated trip length frequency distribution to try to update their values, and we can get the value of f. Can get the value of f in the next iteration, and repeat this process. Again and again until you find that the fm plus 1 is close to fm. If they are close to each other, then you can stop your iteration. So that's the general procedure to conduct the FHWA calibration method. And now let me give you an example to see how the model is how the calibration model is applied. We're going to use the same example in the previous calibration. So we have the trip rate. This is the trip rate, and the cost matrix. So those would be the two observations we have to use. And now, at first, we need to generate the observed trip length frequency distribution based on the true values, based on the observed values. So, for that distribution, we actually need to recall these equations. First of all, we have to specify what's the bins. For the bin definition, you can actually define by yourself, or you can try to use the try to observe the values in this cost matrix. Well, in this cost matrix, we see that the value is changed at every 5 minutes. So so we're gonna have the bin defined as bin 1 is from 0 to 1, 2 is from 6 to 10, and 3 is from 11 to 15, and so on. For all the values higher than 60, that will be bin 13. So that's the bin definition. And now we're going to use this bin definition to see what's the percentage of the trips applied to this, well, how we're going to draw the OTLD figure. So to do that, first we need to identify which cell belongs to bin 1, which would be the trip with the travel time between 0 and 5 minutes. And in this page, you can see that all the cells circled with the right rectangle will belong to cell 1. So here we can see that there are let's see how many trips. So we can try to identify, go back to check the corresponding cells in the trip matrix. So these two will be corresponding cells. And if you summarize all the trips in the trip matrix, you can see there are totally, well, I'm not quite sure about the exact number, but basically, if you do the summary about all the trips in this red rectangle, divided by the total number of trips, we see there are 42.4% of them belongs to the first cell. So that's for bin 1. And with that, you can draw the bar for bin 1. That is 42.4%. And we can all then go to bin 2. The bin 2 will represent the cell with the length from the travel time from 6 to 10 minutes. from the cost matrix, you can only find out 4 cells, and with that you will get the 4 corresponding cells in the trip matrix, and then you can calculate the percentage, which is 14.5%. With that you can get the the bar for the second bin, and similarly you can apply the third bin. You can apply the third bin, the fourth one, the first bin, fifth bin, sixth bin, and seventh, and so on for all the bins you specified. With that, you get the complete observed trip length frequency distribution. This is the complete one. And so that's the first thing. We find out the observed trip length frequency distribution. And next we need to specify the parameters applied for each bin, which would be the F values applied for each bin. So with that, you just need to specify which cell belongs to the each bin. So for bin 1, we have this yellow region as the with the travel time between 0 and 5 minutes. So you put the F value for all those cells. And for the bin 2, we only have 4 cells, and then you put a F2 in this cell. And similarly for F3, you can add 6 more cells: F4, F5, F6, F7, F8, F9, F10. We don't have any cell for 10, and F11, F12, and nothing for 13. So with that, you fill the F values for all the cell, and we're going to use this information to do the calculation. So for the calibration, first of all, we assume that all the F values will be 1. So F1 is 1, F2 is 1, F3, F4, F5 until you get to F13. And this would be the initial setting of the F values. And now you have the F matrix, they all be 1. And next, you need to compute the value of the Tij. So what you want to do is trying to calculate the AI and Bj first. So for AI and Bj, again, you can assume that initially you can assume that sorry, there will be a lot of things I forgot to mention. So you have AI and Bj, and you can do the calculation about the AI and Bj. As you will see that the all the F values will be 1. So in the first iteration, it will be quite straightforward. So Tij hat would just be AI times OI times Bj times Dj. FCij is actually just be 1, so you don't need to put them there. And this is the trip matrix we're going to use. And now for the first iteration, we have initial guess, assume that all the A values would be 1, and then apply this equation to calculate the value of Bj. So do this calculation, you find that all the B values will be the same. And if you do another thing, you find that A will be 1. So for the first step, all the A values will be 1, all the B values would be 0.00093. So that's the result we get from the first iteration. So that's what we get for first iteration. And then we can calculate we can estimate the number of the trips based on these equations. We have A values, B values, and F. So with that, we can get the estimated trip rate. So we find out the value for each cell. And then we can make a comparison. It looks like it's not they are quite different to each other. So it means that you need to do more iterations. They are not close to each other. You have to do more iterations to make sure that they are close enough. So what do we do? What do we do for the iteration? As we're going to use the observed turbulence frequency distribution, and then based on the estimated trip rate, we're going to generate an gravity model estimated turbulence frequency distribution. The generation of this one is the same to this distribution. The only difference, like here, you're gonna use the this trip rate, the estimated trip rate, instead of the observed one, to draw the distribution. And now you have the percentage for each beam, and this comes from the estimated value. We have the true percentage for each beam from the observed value. With these values, you can try to update the value of the f values. So this is the equation you're going to use to update the f values. So the initial guess of f is 1. So we set all the values as 1, and you have the observed. Turbulence frequency distribution. You have the estimated turbulence frequency distribution, and apply this equation. You can update the value of f. So f11 is 1. If you apply this equation, f11 it's a 45.67 divided by 30.48 times f01, which will give you the value as 1.48, and this is for the first cell. And you can do the other calculations, like for this one, this is a f16 equal to 4.75 times 11.93 times f06. f06 is 1, so that will give you the value as 0.40, and similarly apply to for all the other cells. And you can find out the value. You can find out the value of all these beams for capital F, and then you're going to use the updated f value to do the calibration, to find out the values of AI and BJ, and to estimate the trip rate. So to do that, we have the updated f value. We have initial guess of A0, and then in this iteration, you might need to do more iterations about AI and BJ. So for initial guess, A0 is 111, B1 is a point something like this, some other values. And you can do some iteration about apply this equation to get the value of AI, and it looks like these two are not close to each other. So we need to do another iteration to get a B2 and get a A2, B3, A3, B4, A4, and so on until you find that the if there are some two iterations, if they are close to each other, then you're gonna stop. Here in the example, I only show the values, show one iteration, but you need to do more iterations for the homework and anything else, any problems in the exam and project. So with this kind of update, you can get the you can do another estimation of the trip rate, and if we believe that the trip rate is still it's quite close to the observed one, you can stop it. If it's still far away to the observed value, then you need to do another iteration to update F2 and get the A2 and B2 and F3, get an A3, B3, and so on. So you need to do more iterations until you find that. Ideally, you want to find that Fm plus 1 will be similar to Fm. In that case, you can stop the iteration. But here, in the example, I will just stop here, and you can do some practice later by yourself. And now, once you finish the calibration, you find out the converged value of F, you find the converged value of A and B. You can try to find out the errors between the estimated trip matrix and the observed trip matrix. So this table shows the error from the FHWA method, and we can also get the square error, similar to what we did previously. The mean square error is 13.17 compared with the previous one, 9.2 is higher. So we probably can claim that this calibration method did not give us a good result compared with the average cost method. So here, so here you can see the difference. You can see the difference from different iterations under the FHW method. This is from the first iteration. This is from the second iteration. Obviously, you can see that the second one is much closer to the observed value, but the first one is it's just the initial step. It's reasonable to observe this huge difference. We need to have more iterations to make the result converge. And with that, if we want to do more iterations, you need to calculate the estimated trip length frequency distribution. And you can see by this comparison, you can see that with more iterations, this distribution will be much closer to the observed distribution, at least compared with the first iteration. So that's the comparison. What's the effect we get for the FHW method, and we can do more iterations, like from the F1 to F2, we can update it, and the result will be more accurate for you to describe the trip rate. And eventually, once you conduct everything, you will find that for the average cost method, you have all these parameters. You get the values of A and B, and also the estimated value of mu. For the FHW method, you get the value of A and B. Also, you have the value of Fk for all the beams. And this would be the calibration result from these two methods. And now let's go to making a quick comparison about these two methods. This one comes from the average cost method. This one comes from the FHW method. At the current step, this one performs better compared with the FHW method. But if you do more iteration, you will find that both of them will have very good performance. In the example, I just stop at this step. And this page giving a quick summary about what's the difference of the FHW method and the average cost method. The major difference is, like for the FHW method, we assume a random distribution between the a random distribution about the travel time. While for the average cost methods, the travel time actually follows the average cost. The function fk is it's an exponential function. So that's the only difference between the FHWA and the average cost methods. And regarding to the mean squared error, you can clearly see the difference. FHW mean squared average cost method is mean squared error is 9.2, and the FHW method is 13.1. So clearly this one is better. And finally, there are some comments I have to make for the gravity model. In the gravity model, we have two different assumptions. One is based on the average cost function, the other one is based on the general function. For the FHW method, this one can be applied for any functions, as long as if you have the appropriate definitions of the bin, you can find out the model can fit to any distribution, any travel time function. And the for the equation itself, the first four components could be defined as the demand function, and the function f is just defined as the cost function. Also, if we want to make any simplification, you can put an AI and bj together as an aij, which is changing with respect to the origin and destination pair, and it will be more general. And they will be selected to make sure that the constraint for the demand and supply for the origin and destination are all satisfied. And this one is called the this model is called the constraint direct demand model, and it can help us to find out the to calculate the distributions from the for each origin destination pair directly. And that's also the purpose of the trip distribution model. Okay, I think that will be all today. And I would like to reserve some time for the questions and also give you some explanations, descriptions about the midterm exam. So any questions? Any questions for the for this lecture?
Could you please go back to the? I'm confused about how to use the binary variable phi, then calculate the cost function. So could you please go back to the second step of the iteration?
Which page? Which page?
I forget the page, but it's the I think it's the second step of the iteration.
Which method are you talking about? The FHW method?
EPR model.
Okay. Second step, I guess you're talking about this one. This step compute the TIJ.
Yeah, I'm just a little confused how to use the binary variable phi.
Okay. So this one, I guess you're talking about the delta.
Yeah, that's right.
The delta ijk, it's either 1 or 0, and if the travel time, because you have the travel cost table, the cost table, right? The cost matrix.
Yeah.
And if this cost, it's I say that I'm talking about the bin. Say that for the bin one is 0 to 1 minutes, right?
Mm-hmm.
And if the travel time is between 0 to 5 minutes, sorry, from 0 to 5 minutes, then the delta ij is 1. If it's not, that will be 0, right? Yeah. That's the definition. So for the cell for the cell 1, 1, it's 5 minutes. So delta ij, delta 1, 1, 1, it's so delta 1, 1, 1, it's 1. And delta 1, 1, 2, 1, it's 0. So here ij represent the origin and destination. K represent what's the which being it is. So you have delta 1, 1, 1 is 1, then delta 1, 1, 2 will be 0, and delta 1, 1, 3 will be 0, and so on. And for delta for the second cell, delta 1, 2, 1 is 0, but delta 1, 2, 2 actually belongs to the second being from 6 to 10 minutes, so it's 1, and delta 1, 2, 3 is 0, delta 1, 2, 4 is also 0, and so on. Similar thing can be applied for all the cells. And if we have the delta ijk, I from 1 to z, j is from 1, is also from 1 to z, and the k from 1 to I did not define it, from 1 to capital K, the total number of the beings. So that's the definition. So with this definition, you can then have the the detailed expression of the FCIJ. So FCIJ it's a function of the cost. So if Cij belongs to bin, if it belongs to bin k, then that'll be 1. If it's not, that'll be 0.
So in this case, the cost function of the let us just say the FC11. So FC11 is equal to just the F1, right?
Yes, FC11 belongs to is to F1. So basically, what do you get eventually once you finish everything? And let me see. Once you complete everything, I think this F table, well, this F table is just the this F table is just the FCIJ.
Yeah, that's right. So for the specific combination of the origin and destination, let us just say from the origin I to destination J. So we just need to say the travel time I to J, and have a look at which being the travel time will fall in. So
yes.
And the being K, so the FK will be the cost function of the destination of the origin I to destination J.
Yes,
right?
yes.
Okay.
So that's the reason we say that this you have to write down this lookup table.
Okay.
So you can with that you can always find out what FCIJ it is.
Okay. Yeah, I see. Thank you.
So I will post another homework assignment on Emily to Learn, so you can try to do some practice by yourself. And also, I would recommend you to try to follow the examples in this lecture. I haven't go through all the steps, all the iterations. You can you can continue these iterations to see whether you can make the calibration result more accurate I just stop, like for most of the example, I just stop at 2 or 3 iterations, but I definitely need more iterations to get a better result. Okay, any other questions? Okay, if no, then I will give in a very brief description about the midterm exam. For this midterm exam, now it will be scheduled on well next Tuesday from 3 to 6. But even though it don't need the 3 hours, but I try to make it longer. You can. It's an online exam, so you just need to you will be assigned with the exam sheet on every need to learn, and once you well during the exam time you can work on the all the questions. It's an open notes, so you don't need to remember anything, but you have to be familiar about all the course materials. And once you finish all the questions, you need to upload your answer sheet, or put them in the right order, write down with a very detailed page number, upload them on Every to Learn, and I will create a folder there. So you should upload them before 6 p.m. So that's the general format for you to work on the midterm exam. That's one thing. And the second, for the questions in the midterm exam, we have 1, 2, 3. We have 5 questions, which will cover the lecture 1, lecture 0 to 6, not including the one today. Most of them are about the computations, and they are all. I should say that it will be simpler than the problem you are working in the homework, but you have to be very familiar about the terms or some concepts we define in the course notes. Also, when you are working on the solutions or in the questions, you should write down all the details about your computation, especially about the steps. Do not just give the one statement and then jump to the solution directly. Show the calculation steps, and with that, I can give you justify whether you are using the right method to get the result. The points or the marks will be provided to you based on the steps you showed in the exam sheet and the accuracy of your result. So totally 5 questions, and you have 3 hours to work on all the 5 questions. Do not those questions are all simple. Do not think about something too complicated. If you are working on something very complicated, it probably means that you are choosing wrong methods to solve the problem. So anything you want to know about the exam? By the way, for the solutions of the homework 3, I will upload the solution once after the deadline of the submission. With that, you will have some time to review the solutions and work on using the homework to prepare the midterm exam. Any questions you want to know?
Doctor,
Yes.
homework 3, I just wanted to confirm. So in the actual PDF, I just wrote down the answers, but I also submitted my R Markdown file where you can see like the steps that I followed. Is that okay?
That should be fine as long as you well, it should be okay. I'm gonna check all the files you uploaded.
Okay.
Yeah.
Okay,
If you
yeah,
think there are some files you don't want me to see, then you can delete it from your submission.
no,
But
that's okay. Yeah. I just submitted the coding for problem 1 and then the Excel sheet for problem 2 and 3 because I did it through Excel, but I didn't explain like the steps in the PDF, you know?
Okay. Well, it's better for you to show the details. But if you can find anything in the Excel or any other place, it's also fine. For the homework, it's probably fine because I have. Well, I can try to explore more details. For the exams, I would like to see some clear steps.
Yeah. Okay, dear, perfect. Okay, dear, thank you.
Okay. Any questions? If no, then that will probably be all today. We still against half an hour. But just feel free to contact me if you recall any questions or if you want to know more details about the exam. Feel free to contact me, and we will start our exam on time next Tuesday. Okay. Well, I think that should be all today, and well, I hope you all have a good week, and I will see you next Tuesday for the exam.
Thank you, doctor. Have a good week.
Okay, great. Thank you. Enjoy your day. Bye.
Thank you. Bye.
Thank you.
Excuse me, Professor.